Thank you. And I'd like to thank the organizers for all the effort they've put into this conference. I should also say that everything I'm presenting here is joint work with my advisor, Koebe. So I'm going to start by introducing what I mean by Koebe uniformization. So uniformization questions, roughly speaking, ask when spaces are equivalent to some sort of model space. In this context, it classically started with asking when domains in the plane are conformal to some given model space. So the Riemann mapping theorem is a classical theorem where your model space is the disk. And it states that if you have a simply connected domain, which is a proper subset of the plane, then it's conformal to a disk. Here, conformal is referring to an angle-preserving homeomorphism. So we do require that it's injective and surjective and all that. And then, of course, you've got that every simply connected Riemann surface is conformal to either this Riemann sphere, the plane, or the disk. This is also a classical result in the forms of this uniformization. And you can ask if these results extend to cases when you're not necessarily simply connected. So the model space that we consider in the not simply connected case are called circle domains. So a circle domain is, an open connected subset of the plane where every boundary component, every connected component of the boundary is either a circle or a point. And I've sort of drawn a picture here, but it could be unbounded as well. You could imagine just a bunch of like disks sitting inside the plane and you're looking at their complement. Koebe actually conjectured that every domain was conformal to a circle domain and proved it for the finitely connected case. So if you have finitely many boundary components, then you will be conformal to a circle domain with finitely many boundary components. And in 1993, Hay and Schramm were able to prove this for countably connected domains. However, the general case where you have uncountably many boundary components is still open. So this is the Koebe uniformization in the conformal case, but more modern versions of this investigation ask the same questions, but change conformal to quasisymmetric. So let me define quasisymmetric for you. So suppose you have a homeomorphism between metric spaces. The nicest possible thing you can expect it to do is to completely preserve the metric structure. And that's what an isometry does. So if distance is preserved between the metric spaces, our homeomorphism is an isometry. Not all maps are this nice, and it's useful to also look at bi-Lipschitz maps, where you require that the distance is preserved by multiplicative up to a multiplicative constant, but not necessarily exactly preserved. So a quasi-symmetric map is a weakening of this. And the definition I give here isn't exactly quasi-symmetry, but it's equivalent for most of the cases we're going to be looking at in this talk. So we say this map is weakly quasi-symmetric if when you pick any 3 points, if you dictate that the ratio of the distances is bounded above by 1 in the domain, then you have some sort of bound in the range. Here's sort of a picture of what's going on. So my x2 is going to be closer to x1 than x3 is. That's this condition that the ratio of the distances is less than or equal to 1. And then the idea is that when I map it into the domain, I need this distance, capital L, over this distance, lowercase l, to be bounded above by some uniform constant. And the worst case scenario, right, is when this circle is mapped onto this shape right here, that you sort of want to look at the maximum distance you attain over the minimum distance you attain, and you require that to be bounded globally. And this is kind of related to the idea of conformal maps, because for a map to be conformal, you only require that this happens on a local level. If you require that this happens locally, that sort of infinitesimal circles get sent to infinitesimal things like this with bounded eccentricity, that's called quasi-conformal. And if you require that the ratio capital L over lowercase l equals 1, then that's conformal. And that aligns with the classical idea that sends infinitesimal circles to infinitesimal circles. So the first big result in uniformizing planar domains with quasi-symmetries is a famous theorem by Bonk and Kleiner. So if you start with a metric space, which is homeomorphic to this sphere, the sphere with its standard metric as inherited from R3, and you require that it has this condition called alpha 2 regularity, then you have that your metric space is quasi-symmetric to the sphere if and only if it's linearly locally connected. So that alpha 2 regularity just means that the Hausdorff 2 measure of a ball is comparable to the square of its radius. And then the linear locally connected, I'll kind of skip over the details of this, but roughly it states that you have no cusps and you have no really thin parts. It's a geometric condition that you impose on the space. And the details I want to draw attention to here are the fact that alpha 2 regularity is a property which is not preserved under quasi-symmetries. And for example, you can have quasi-symmetric images of the sphere, which are not alpha 2 regular, even though the sphere itself is alpha 2 regular. And linear local connectivity is a quasi-symmetric invariant. So the image of a space that's linearly locally connected under a quasi-symmetry will also be linearly locally connected. Now, once again, you can ask if you can extend these results to the case when things are not simply connected. So to do that, we have to talk about geometric properties of the boundary of your space, in particular ones that will be preserved under quasi-symmetries. And to do that, I'm going to introduce this notion of relative distance. So relative distance between two continua in some metric space, you just take their distance divided by the smaller of the two diameters. And how I think of it is sort of with this picture. So if our E here is this red slit and our F is this blue slit, you can imagine zooming in until, if your screen, say, is height 1 and you zoom in until the red slit occupies the length of your screen, then you sort of pull out a ruler and measure the distance to the blue slit. That's your relative distance. So, two things could be very close, but still have a very large relative distance because the smaller one could be very small. In general, we say that a collection of continua in a metric space is uniformly relatively separated if pairwise you have a uniform lower bound on their relative distance. And so the first result we have here, uniformizing not simply connected domains, comes from a theorem of Mario Bonk, where he does require that you have a collection of uniformly relatively separated uniform quasi-circles. Here, a uniform quasi-circle just means that the boundary components are quasi-symmetric images of circles, and that the H for each of these quasi-symmetries is uniform across all of them. And we're looking at this as sitting in the sphere. So there will be a quasi-symmetry with these assumptions that sends all of these Jordan domains essentially to round disks. And I should note here that this theorem is actually more general than applying to domains, because it will also apply to, for example, if you have round carpets, things that are homeomorphisms of the standard Sierpinski carpet, also fall under the umbrella of this theorem. So it's much more general than just dealing with domains. But you can also ask, if you do assume domains, can you extend this to the more general metric space setting rather than assuming that you're in the sphere? And there's a paper by Marenkov and Wildrick where they showed that if you're homeomorphic to a finitely connected circle domain, and your metric space is alpha 2 regular, which is the same condition that was in the Bonk and Kleiner theorem, then you're quasi-symmetric to a circle domain if and only if you're linearly locally connected and the completion is compact. And a more complete characterization has recently been given by Ryla and Rasmus. I say more complete here because Marenkov and Wildrick assume alpha 2 regularity, which varies under quasi-symmetries, whereas they replace that with this condition here that X carries a weak metric doubling measure. I won't go into what that means, but it is a property which is invariant under quasi-symmetries. Now, if you want to move to general metric spaces beyond the finitely connected case, like moving up to the countably connected case, Marenkov and Wildrick also had a result for that. And this is a really technical statement. So again, I'm going to just try to give you some details here. These conditions A, B, and C that they impose on their space are not invariant under quasi-symmetries. These conditions 1, 2, and 3 are all invariant under quasi-symmetries. So if your space satisfies these conditions A, B, and C, then you're quasi-symmetric to a circle domain if and only if you satisfy conditions 1, 2, and 3, which are invariant under quasi-symmetries. And in this paper, they actually stated that they're very interested in seeing if you could replace these conditions, A, B, and C, with ones which are invariant under quasi-symmetries. And the theorem that I want to present to you today, that my advisor and I approved, replaces 2 of these conditions. It drops B and C and has this new condition to replace the L-force 2 regularity. So if we have a metric space that's homeomorphic to a countably connected domain in the sphere, and we have that the Hausdorff 2 measure of any ball locally is bounded above by R squared, then we're quasi-symmetric to a uniformly relatively separated circle domain if and only if your boundary components are uniformly relatively separated. The completion is compact, and then here X has the 2 TLP. So the goal of the rest of my talk, in the next 8 minutes it looks like, is to define what this 2 TLP means, because it's this 2 TLP really that replaces these conditions B and C from the Minkowski-Wildrich theorem. And to do that,
Jonathan, feel free to take a little longer since we usually have some time left at the end anyway.
Okay, sure. Yeah. So, so to work towards defining 2 TLP, I need to introduce some of the classical tools to work with conformal maps. So the first of these is the notion of modulus. So first we start with a metric space, homeomorphic to some domain in the sphere, and we look at a collection of curves in our metric space. So if you take some Borel function on your space, you can say that it's admissible to all of these curves if the line integral over each of these curves is at least 1. The modulus of this family of curves is then defined as the infimum of the area integral over your space of all such admissible Borel functions. And this is useful as a tool with conformal maps because it's a conformally invariant quantity. So if you have a collection of curves and you look at the collection of curves that is the image under a conformal map, they'll both have the same modulus. And you can think of it like an optimization problem, because you're trying to minimize this area integral while you're under the constraint that all of your length integrals are at least 1. And sort of an intuition for how modulus works is that if your curves are long in length and few in number, then the modulus is small. In other words, if you have a family of curves and you make them all longer, you decrease the modulus. And if you remove some of the curves, you will also decrease the modulus. So here's sort of a picture of what's going on. So oftentimes, for this context, the family of curves that we're considering the modulus of will be curves connecting disjoint continua. So in this picture, my red splotches here are just 2 continua sitting inside your space. And then these blue curves are the set of all curves connecting the 2 continua. And we're interested in the modulus of this family of curves. And in particular, we're interested if this modulus can be bounded below by some function of their relative distance. So if you can always bound the modulus of curves connecting 2 continua below by some function of the relative distance, we say it satisfies the Levner property. And it turns out whether or not a space satisfies the Levner property will be a quasi-symmetric invariant. So as long as your spaces are satisfying sort of the same regularity conditions. And this Levner property is a good way to characterize sort of when local behavior becomes more global behavior. Now, there's a variant of modulus, which was actually introduced by Schramm, who's the same person from the theorem K and Schramm, where they showed that every countably connected domain is conformal to a circle domain. And he introduced this to try to prove that, although his proof ended up working out differently. And that's this idea of transboundary modulus. So the idea is that now you look at a family of curves that you're still trying to assign some quantity to, but you allow them to pass through some components that say are part of the boundary of your space. So the idea is that you look at a family of curves and a collection of continua in your space. And now with admissibility, you only care about integrating your Borel function outside of these continua. And then you just add some fixed weight for any of the continua that it happens to intersect. And you require that this is at least 1. And then the transboundary modulus is just infimizing, again, the area integral outside of these fixed continua, and then adding up the squares of all of the weights. And this is sort of the picture of how transboundary modulus looks to modulus. So here I made the boundary components gray to sort of indicate that you can pass through them. And as these blue curves, you'll see as the blue curves pass through the boundary, you don't actually care how long they live in the boundary or what their integral will be there, because you're just going to add a fixed weight for each time they intersect it. So in that sense, they're allowed to just skip across the boundary as long as they sort of pay that fixed weight. And then you can define a similar notion to the Leibniz property by the transboundary Leibniz property, where you just require that the transboundary modulus of curves connecting two continua is bounded below by some function of their relative distance. This will also be invariant under quasi-symmetries. And in general, you can say that if the space has a Leibniz property, then it's going to have the transboundary Leibniz property. And that's just because the transboundary Leibniz property includes all the curves from the Leibniz property, right? You have these ones which don't touch boundary components at all, but it also throws in more curves which are allowed to pass through the boundary components. So it's in general bigger, and so the Leibniz property will give you the transboundary Leibniz property. However, it turns out that, for our purposes that we were analyzing, it turns out that the transboundary modulus would end up being too big, and the modulus would end up being too small for our purposes. And the right quantity to look at is something like a mixed modulus, where you sort of combine the two approaches, where you allow yourself to pass through some of the boundary components, but not all of them. And that's where you introduce this in-transboundary Leibniz property. So the idea of the in-transboundary Leibniz property is that it's just like the transboundary Leibniz property, except you restrict your family of curves to only connect E and F and dodge particular boundary components. So you select in, for any selection of in boundary components, you look at the family of curves connecting E and F, which dodge all in of those boundary components. And you require that that transboundary modulus be bounded below by a function of their relative distance. So in this picture here, these two components are black, which means that you can't pass through them, but you can pass through the gray ones. And this is an example of having a 2 transboundary Leibniz property, because we have avoided 2 of the boundary components. This will also end up being a quasi-symmetric invariant. And in general, you get that having an n+1 transboundary Leibniz property gives you an n transboundary Leibniz property. Because again, you're considering the n transboundary Leibniz property is a larger class of curves, which is always going to be larger. And another thing I want to emphasize here is that this has to hold true for any selection of boundary components. So here I've selected these 2, but I still need that same lower bound on the transboundary modulus for the selection of any 2. So here would be another example where I've selected 2 different ones. It's kind of hard to see, but this really eccentric ellipse is also black. So my curves have to dodge this boundary component and this boundary component. I still expect the same lower bound for any 2 boundary components I pick. So this in-transboundary Leibniz property turns out to be the right thing to consider. And how it relates to circle domains is that all circle domains will have the transboundary Leibniz property and the 1 transboundary Leibniz property. But it turns out they only have the 2 transboundary Leibniz property if they're uniformly relatively separated. And in this case, they'll have the in-transboundary Leibniz property for all n. So this is starting to resemble Marenkov and Wildrick, where they required that uniform relative separation. And then it turns out that domains in the plane whose boundaries are uniform quasi-circles will have the 2 transboundary Leibniz property if and only if they're uniformly relatively separated boundary components. This follows from the paper of Bonk. And in general, though, your 2TLP and 3TLP, for example, are not equivalent because you can always find an example of a domain which has the in transboundary Leibniz property, but not the n+1. And so this is what it means by the 2TLP in the statement of the theorem. You require that it has the 2 transboundary Leibniz property, which turns out to be exactly the right property you need to get this uniform.